Welcome to AI Frontiers, your guide to cutting-edge research in artificial intelligence and robotics. Today we're exploring a robotics revolution where AI meets physical intelligence. On June 29, 2025, 14 groundbreaking papers were published that collectively showcase fundamental advances in how we think about robot intelligence, safety, and capability. These aren't just incremental improvements. They represent transformative breakthroughs spanning from safe autonomous systems to intelligent manipulation, revealing how AI is revolutionizing physical robotics capabilities. Join us as we discover insights into tomorrow's robotic intelligence. Today's journey takes us through a comprehensive exploration of revolutionary robotics research. We'll examine 6 dominant themes that are shaping the current landscape of robotics, from mathematical breakthroughs in robot safety guarantees to sophisticated AI systems that enable robots to understand complex physical interactions. Our deep dive will uncover cutting-edge advances in human-robot collaboration, examine how modern manufacturing is being transformed by intelligent systems, and spotlight 3 pivotal papers that are defining the future direction of robotics research. This analysis reveals a field undergoing rapid transformation, with researchers developing increasingly sophisticated solutions to complex real-world problems. Computer science robotics represents one of the most fascinating intersections in modern technology, living at the crossroads of artificial intelligence, computer science, and physical systems. Unlike traditional robotics focused on mechanical engineering, this field bridges discrete computation with continuous physical dynamics, requiring real-time decision-making where consequences affect the physical world. Researchers must possess multi-domain expertise spanning algorithms, control theory, and perception while grappling with challenges that simply don't exist in purely computational domains. This interdisciplinary foundation is crucial as we approach widespread robotic deployment across industries, from manufacturing and healthcare to agriculture and domestic services, where intelligent machines must work alongside humans as capable partners. The first major research theme focuses on safe and robust control systems, moving beyond heuristic safety measures to formal mathematical guarantees. As robots transition from controlled laboratory settings to real-world applications where human safety is paramount, researchers are developing sophisticated frameworks that combine model predictive control with reachability analysis integration. These systems provide provable safety constraints while simultaneously optimizing performance, creating ironclad safety guarantees even in uncertain dynamic environments. Applications span from autonomous vehicles navigating construction zones to robotic manipulators working in close proximity to humans. Wang and colleagues demonstrate a breakthrough safety performance framework that represents a fundamental advance in ensuring autonomous systems behave safely while achieving their intended objectives effectively. Adaptive learning and multimodal perception represent critical themes driving modern robotics forward. Rather than simply replacing traditional control methods with neural networks, researchers are developing sophisticated hybrid approaches that combine the reliability of classical control theory with the adaptability of modern AI. Neural networks are learning to predict physical dynamics and master complex motor skills, while multi-sensor fusion integrates information from cameras, LiDAR, event sensors, and proprioceptive feedback. Huang and colleagues pioneer transformer-based world modeling that handles multi-object, multi-material scenarios seamlessly. The real challenge lies in creating robust understanding through uncertain multimodal information processing, developing new mathematical frameworks for representing and reasoning about complex sensory data to achieve comprehensive environmental understanding. Human-robot collaboration and manufacturing innovation showcase practical applications driving research progress. Modern collaborative systems require sophisticated behaviors that extend far beyond simple collision avoidance, involving the prediction of human intentions in shared workspaces and enabling seamless object handoffs between humans and robots. Manufacturing applications are pushing boundaries with mobile additive manufacturing systems, creating complex structures in place, and dual-arm manipulation systems, handling intricate assembly tasks. These solutions improve efficiency, flexibility, and quality in production, while adapting to changing requirements and conditions. Supporting this progress are advanced simulation platforms, enabling complex multi-agent interactions, providing essential tools for developing and validating new algorithms before deployment on real systems, becoming increasingly important as the field moves towards standardized evaluation methodologies. The research papers present several breakthrough discoveries. that are fundamentally reshaping robotics capabilities. Formal safety guarantees for dynamic autonomous systems now combine model predictive control with Hamilton-Jacobi reachability analysis, providing mathematical certainty about robot behavior in unexpected situations. World models can now predict complex multi-material interactions, handling rigid objects, deformable materials, and flexible components within unified frameworks. Event-based sensing achieves superior visual odometry performance compared to traditional camera approaches while requiring fewer computational resources. Researchers have solved mode collapse problems in multi-agent trajectory prediction, crucial for autonomous vehicles and systems predicting human behavior. Additionally, adaptive assistance mechanisms accelerate motor learning in humanoid robots by 30% while significantly reducing failure rates, demonstrating how learning-based approaches can be effectively integrated with traditional control methods. The methodological innovations driving current progress demonstrate remarkable sophistication in addressing complex robotics challenges. Model predictive control with Hamilton-Jacobi reachability analysis provides mathematical guarantees about safety while optimizing performance, though it requires accurate system models and can be computationally intensive. Transformer architectures adapted for physical dynamics modeling represent world states as token sequences, learning complex dynamics directly from data without requiring detailed physical models, though they need large training datasets. Differential flatness enables analytical control solutions for systems possessing this mathematical property, transforming complex trajectory planning into simpler algebraic problems. Voxel-based spatial representation provides efficient three-dimensional processing for mapping and path planning, while curriculum learning with adaptive assistance mechanisms accelerates robotic training by providing shaped guidance that helps robots explore productive regions of the state space. Lang and colleagues' work on safe and performant autonomous systems represents a fundamental advance in deploying systems that are both safe and high-performing. Their methodological approach combines model predictive control with Hamilton-Jacobi reachability analysis, using reachability analysis to compute backward reachable sets representing all states from which systems can be guaranteed to remain safe. These sets are incorporated as constraints in model predictive control formulation, ensuring optimization only considers control actions maintaining the system within safe reachable sets. The framework guarantees recursive feasibility, meaning if a feasible solution exists at one time step, it continues to exist at subsequent steps. Validation through simulation studies using four-dimensional Dubin's car models and 6 degree of freedom KUKA robotic manipulators demonstrates significantly improved safety constraint satisfaction, while maintaining competitive task performance, providing a general approach applicable to various autonomous systems. Huang and colleagues introduced particle former, a transformative approach to understanding and predicting physical dynamics in complex robotic manipulation tasks. Their methodological innovation adapts transformer architectures to physical dynamics prediction, representing entire three-dimensional scenes as token sequences encoding object positions, velocities, material properties, and interaction forces. The particle former architecture processes these sequences using attention mechanisms capturing complex spatial and temporal relationships between different objects and materials. A key innovation is the hybrid point cloud reconstruction loss function, supervising both global and local dynamics features, enabling the model to capture large-scale scene dynamics and detailed local interactions. The training process uses real-world robot perception data directly, without requiring elaborate three-dimensional scene reconstruction, representing a significant practical advantage that opens new possibilities for manipulation planning and control in multi-material environments. Event-based visual odometry represents a revolutionary breakthrough in sensing technology for mobile robotics. Event cameras respond to brightness changes rather than capturing traditional frames, offering unique advantages including high temporal resolution and dynamic range. Recent algorithmic developments enable effective processing of event streams for visual odometry, achieving superior performance compared to traditional camera-based approaches while requiring significantly fewer computational resources. This breakthrough enables more efficient and robust perception systems for mobile robots, particularly excelling in challenging lighting conditions or high-speed scenarios where traditional cameras struggle. The technology represents a significant advance in mobile robot navigation, potentially transforming how autonomous systems perceive and navigate through their environments by providing more responsive and energy-efficient sensing capabilities that maintain high accuracy across diverse operating conditions. Future directions in robotics research reveal exciting opportunities and persistent challenges that will shape the next generation of intelligent systems. The integration of formal methods with learning-based approaches promises to combine mathematical rigor with adaptive capabilities, while scalable multi-agent coordination frameworks will enable complex collaborative behaviors across multiple robotic systems. Real-time adaptation to unknown environments and materials remains a critical challenge, requiring systems that can rapidly learn and adjust to novel situations without extensive retraining. The development of standardized benchmarks for reproducible robotics research is becoming increasingly important as the field matures, providing common evaluation criteria that enable meaningful comparisons between different approaches. Perhaps most significantly, bridging the simulation-to-reality gap for complex behaviors continues to challenge researchers, as systems that perform well in simulation often struggle when deployed in real-world environments with their inherent unpredictability and complexity. Transparency in our research analysis process is essential for maintaining credibility and enabling reproducibility. This synthesis was created using advanced AI systems, including GPT and Claude Sonnet 4 2025-514, ensuring comprehensive coverage of the technical content while maintaining accuracy in complex domain-specific information. Text-to-speech synthesis is powered by DeepGram technology, providing natural and clear audio delivery optimized for technical content. Visual content generation utilizes Grok image generation capabilities to create relevant and informative graphics supporting the podcast narrative. Human expert review was conducted throughout the process to ensure accuracy and completeness of the technical analysis. We acknowledge that potential oversights may exist despite our careful review process, and we provide complete references to original research papers to enable listeners to verify information and explore topics in greater depth. Join the AI Frontiers community and stay at the forefront of technological innovation. Subscribe to our YouTube channel for weekly research updates featuring deep dives into the latest AI and robotics breakthroughs. Our expert analysis covers emerging technologies and trends, connecting you with researchers and practitioners worldwide who are shaping our technological future. Be part of the conversation that's defining how artificial intelligence and robotics will transform industries and society. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprintserver.org.